this point corresponds to loops generated very recently. And since the number is less and less compared to the early universe, we have a decrease here. And as you can see, if we change the tension of cosmic string, the amplitude change. So if the tension is small, amplitude decrease. And also you see the frequency change. So typical frequency change. If you consider small tension, the spectrum is seen only at high frequency. It's because this tension also becomes lifetime of loops. So it means that if tension is low, lifetime of loops is long. So there are more small loops surviving in the universe. So that's why we can have more high frequency loops. But because of that, also the amplitude of gravitational emission is proportional to g square. The amplitude itself will go down. And here is the figure for different alpha initial loop size. And initial loop size, roughly speaking, initial loop size determines the typical amplitude, typical frequency. So for small alpha, which means the loop is very small at the generation, you get a high frequency gravitational wave. And this red line have different behavior because this alpha also affects the lifetime of loops. So in this red case, because alpha is large enough, cosmic string loops survive for a while. But in the other case, cosmic string loops disappear soon after generation because original energy of cosmic string loops is small or small alpha, and they disappear soon after emitting gravitational wave. So they disappear soon. So that's the difference in evolution is this difference. And the effect of deconnection probability only changes the amplitude. So basically, as I explained there, if you have small reconnection probability, there are more strings inside the universe. So it enhances the amplitude of gravitational wave. It just increases the number density of loops. So yeah, so by thinking around all the parameter space, this is the accessible region by experiments. So this dotted line shows the accessible region by fast search, and this solid line corresponds to accessible region by gravitational wave background, stochastic gravitational wave background. So, for example, let's see, in the case of advanced LIGO. So this fast search and stochastic background search gives different constraints. So depending on vertical axis is the G and the horizontal axis is alpha. So depending on the typical loop size, this advanced LIGO can give so this fast search and stochastic background search give complementary constraint. The important point for LIGO is that it's useful for small alpha regions. So SK is future pulsar timing experiment. for large alpha. But the good point of advanced LIGO is that they can be constrained on the region of small alpha. This is because when you change alpha, there is a spectrum goes to high frequency. So the sensitivity curve of the SK is here, 10 to minus 8 Hz. And the LIGO has sensitivity around 100 Hz. So in terms of frequency, LIGO have more advantage. So you always expect a high frequency gravitational wave. As you guess. The gravitational wave is always with at high frequency, 20 parameter. So in that sense, LIGO has an advantage of exploring more parameter space. Okay, and this is to draw this figure, I fixed the reconnection probability is 1. So it's more for phase transition origin screen. But of course you can change the reconnection probability and draw the same figure. So in this figure I assume the p equal 10 to minus 2. And as you can see, the constraint is much stronger. By the way, this colored region is already constrained by current experiment. So as you can see, compared to the case of T equal 1, the case of T equal 10 minus 2 is much stronger. This is simply because small p enhances the gravitational wave spectral amplitude. And here I show theoretical lower limit for cosmic superstring tension. So there is a theoretical lower limit for only the case of cosmic superstring. So if we can exclude all the region, then this cosmic superstring have a problem. So by putting constraint using gravitational wave, we can provide a very important information to the model building of inflation in terms of superstring theory. So that's all my talk. So in summary, yeah, gravitational, the message is the same. Gravitational wave can become a powerful probe of the early universe. And yeah, maybe I'm running out of time, so I skip summary, but just one message. So as I talked, as I said in the beginning of the talk, new window of observation has just opened. And I think there are still many things to explore in future, including cosmological gravitational wave. And I heard that there are many people from outside of the field, so people are originally not familiar with the gravitational wave. But as you can see in my talk, this early universe gravitational wave is very related to high energy physics. So I think people from other field is very welcome, and you can give some new insight, new inspiration to us. So I'm looking forward to the future collaboration. So that's it.
Any questions? So can you a brief comment about the strategy of finding how to do the data analysis with cosmological cosmic gravitational wave spectrum?
Okay. Yeah, I didn't explain, so it's very signal of gravitational wave background.
But I think like CMB is kind of a uniform background, especially for cosmological one, right?
Yeah.
So usually if we have the build, for example, we build some detector but it cannot move around.
Yeah.
Then I will just simply cannot tell it's from the noise. I cannot tell it's from noise. Just like at the beginning, people finding the CMB, they are not so sure it's noise or something else. And then later they find it's come from everywhere. It's uniform, so they recognize this maybe some meaningful background for cosmology. But I think I will imagine we have the same thing for cosmic gravitational wave background. If we only look for one direction, we may not tell from the noise. But if we can look around the sky and find it's the same pattern from every direction, then we may recognize it as a cosmic background. But at this stage, it seems it's not possible to do this, right?
Yeah, I think so. So I guess what people do in the case of CMB is that they confirm with different experiments. Then they leave.
Yeah.
So in that sense, you can do it also with gravitational wave. Like if it's detected with both LIGO and Tabula, then you can probably say that it's gravitational wave background. But the good thing of this correlation analysis is that you can go beyond the noise curve. So, I mean, it's like template search. You do something similar to template search. So even if it looks like it looks hidden inside the noise, you can extract the signal. That I think that is very characteristic of cross correlation analysis.
More question? If not, we thank the speaker. Now we will come back around